exploited this. Very few people have exploited this, and that's a shame. And where actually all these ideas of fusion categories and all that came back into physics, a lot of them had their origin in physics, but where they really came back in force in the last 10 or 15 years was in all this people studying topological quantum computation. And that got people like me thinking about non-invariants, and I knew all this other stat mech stuff. And so my quest has been to exploit this in some venerable problems in statistical mechanics. And the moral of the story, and what's this sounds trivial to mathematicians studying categories, but for the stat mech people, there's a really important moral, which is draw pictures and your life becomes a lot easier. So the kind of stat mech models I'm going to be discussing are fallen roughly into three categories. I'll mainly discuss the first two with an emphasis on the middle, although using intuition for the first. So the first one is a geometric model, and I'll give a very precise example of what's called a loop model. Maybe more famous in the stat mech world are models based on spins or heights. You've, I'm sure, heard of spins and the Ising and Potts models, maybe not some more esoteric models called the hard square model and the height models in general. And I'll explain what those are as we go on. A limit I won't say much about except occasional comments, but where the quantum condensed matter people are interested in these quantum Hamiltonians for particular spin models, and have been renamed Enneon chains in recent years. So let me go way, way back to 1971, if you can see up on the top there. Oh yeah, so I have a cursor. So 1971, there's this amazing paper written by Temperley. There's a Wales connection, so even though we're all over, since the seminar is being hosted in Wales, this is highly appropriate. So Temperley-Lieb wrote this now extremely famous paper, but at least based on my random sampling of lots of mathematicians and physicists who are studying these knot and link invariants in various applications, a very small percentage of them actually know what Temperley-Lieb were thinking about when they invented their famous algebra. And so that's a bit of the abstract there. So so what they're doing is thinking about statistical mechanics. They're doing this in the transfer matrix approach. So they're thinking about operators acting on some vector space. This is why the extension to Hamiltonians is usually straightforward. They're computing some interesting objects that people have been thinking about. The Whitney polynomial name has died out. Mathematicians now mainly call this the Tutte polynomial, but a physicist would call this the Potts-model partition function. And one thing I can emphasize is those two are exactly the same thing. It's not an analogy or anything like that. The Tutte polynomial is identical to the Potts-model partition function. So I hope everyone in the audience knows what at least one of those two things means. And so, okay, they're studying those models, but what they do via procedure I'll say something about is related to some other models. And that's, again, what people called in those days more the ICE model. In this day, it's usually called the six vertex model, and the Hamiltonian version is called the XXZ spin chain. And that's what they did. And how they did this was to show that you could take these transfer matrices and write in terms of operators acting on a vector space. And these operators obeyed the same algebra. And with some care, it takes a lot of care, but then you can relate the partition functions of the different models. And obviously, once you've done that, then you can prove various interesting things, how they correspond between the two models. One example that people have probably heard of in the Potts models, this I believe was the first way people understood why Potts models with the number of components, the Q states, the number of states was greater than 4 were not critical. And this was the first kind of way people understood that, if not proved it rigorously, but understood it via this mapping of Temperley-Lieb. Okay, so then the same year, it's one of these things about science that always amazes me, is that different people doing seemingly different things seem to get different pieces in what we now see as a big puzzle at the same time. So in the same year, 1971, Fortuyn and Castelline were studying various models. And again, you see in there the Ising model, Ashton-Teller-Potts, which is another Ashkenteller's another one. And it's dichromatic, and there they use Tutte instead of Whitney. So they're relating these, and they notice this. And then they are also related to another thing, what they call the random cluster model. Now, it's more common to call this a loop model. You make loops simply by just drawing the loops that surround the clusters. So they're one and the same model. It's a non-local model, so you have to worry about these things. So they're trying to understand these things. They came up with this beautiful graphical way of understanding this model. And basically, this looked around for a few years, so now we're up to 1975. People basically put this together, Baxter, Caland, and Wu. Fred Wu was a great mathematical physicist, stat mech person who just died a few months ago. Happily, Rodney Baxter is still with us. Anyway, so they related the two things, the geometric models that Fortuny and Castelline were mostly interested in, and this algebraic approach due to Temperley-Lieb. So what you see here, and so what I want to draw, so I mentioned the loop. So the point is, I said the loops around the cluster, so a line from I to J is part of the cluster, and then the loop, they're drawing it with corners, but the loop surrounds there. And then if there's not a cluster there, then the loop goes that way. So that's a key thing for our talk. Basically, if you're having this lattice and we're doing what I would call a completely packed loop model, there's two ways these loops can avoid each other. And then this talk, except for a few slides, will always stick to doing these models on the plane. Okay, so let me now define precisely the models that I want to do. So are you seeing, is everybody seeing David because it's on my screen? Are they seeing, David's on my screen.
I think everybody sees your transparency on the left.
Okay.
And then on the right-hand
side. Oh, okay. So it's not blocking the view. Okay.
No.
That's fine.
On the right-hand side, you can either see the speaker
or the other
or the gallery view.
Okay. Yeah. Sorry, I had something different going on, but that's okay. Okay, good. So anyway, right. So here's the models that I just gave a historical introduction. So let's be precise. So say it's a completely packed loop model. That means you, on every edge of some lattice, I drew the square because it's easiest. I draw a loop, and that's what these lines are there. And at every vertex of this lattice, they avoid or they avoid in one of the two directions. I put these dots in there just to orient you, but that's just the dual lattice. And now the partition function, and as in all stat mech models, you sum over all the configurations. So you sum over all these loop configurations, which just means you pick at each vertex the way the loops avoid, and then you give it a Boltzmann weight, this thing here. It's some number D to the number of loops, and then there's a weight to make it a little more interesting. You can give it a local weight that just tells you if you avoid in this vertical fashion, I give it a weight V, and if I avoid in a horizontal fashion, I give it a weight H. And so that's what the up there means the number of vertical avoidances, number of horizontal avoidance, V and H are just some numbers. And then you sum over all things. And so so you can think of this partition function here as being some topological weight. So the key thing to notice, this D is a number, it's the weight per loop. And that's topological because, or it's non-local. Because to know whether a loop is connected, you have to follow it all the way around. So you have to follow all the way from there to there to see that this loop, these are a part of the same loop, and I give it one. So it's non-local weight, and it depends only on the topology. So it's just the number of loops. And then there's these local weights, the V and the H. And all the models, all the geometric models that I'm going to talk about today are of this form. I'll mainly confine myself to this one. So let me write it in a little more stat mech-y kind of way, heading towards a transfer matrix, if you know what that is. So instead, I'm thinking, so at every vertex, I draw this thing. I say, well, okay, at each vertex, there's two things that happen. I have the weights V if it avoids this way, H avoids that way. So I draw this picture like this, and I just put in a parameter U because it'll be useful in a few minutes. So an overall constant doesn't really matter. We can scale it away. So really think of these as weights as functions of one parameter, V of U and H of U. Make that U the one parameter. So now the same partition function, what I wrote at the bottom again here, I talked about in the previous slide, is I can just rewrite in this fashion, which now heads much more towards the category story that most of the people here know. And so what's going on is then I can then just plug in. So I draw a picture like this. So this is my square lattice, and I pick some boundary condition that I'm not going to worry too much about. So I tie the loops together at the end. But the key thing is when I do is when I plug this in, what it means is when I have this thing eval, I say plug this thing in with the appropriate weights. So I get 2 to the v terms for v vertices. And then so expand that out. And then eval means to anytime I have L loops, I give it a weight d to the L loops, or the number of loops. And then for the number of horizontal avoidances, I give it h for number of vertical. So this slide is literally identical to the previous slide, just written in a different way. So I should pause momentarily. Is that clear? I hope. Any confusion on that one?
What's eval means calculate the number of loops and raise that rate d to the number of loops?
Yeah, we'll expand the whole thing out so you get a bunch of terms and then calculate the number of loops in each term. But that's right.
Okay.
Good.
And it gives you the v's and the h's because of the vertex.
Yeah, and the v's and h's that I stuck in. Yeah, so you have to v, yeah. So nothing subtle. I mean, I hope there's nothing subtle I've done yet. Maybe I'll do something subtle later. But okay, good. So that's the model. Hold that in mind. So we're still on the same model. And again, if you want to think of this algebraic, like I said, think of a transfer matrix if you like transfer matrices, or you can just think of this vector space. And the vector space is you have L strands, and I make an algebra. And the generator of the algebra says, well, I take 2 neighboring strands and I can just fuse 2 of them together and then leave nothing and then undo that. And that's the generator of the algebra. The other generator, which is the identity, don't do anything. And if we label the strands 1 through L, then the EJ does on the JJ plus 1 strand. So then what the algebra just says is if I do E twice, I get back basically the same thing, but I have this loop in the middle. But when we evaluate it, we just replace it with that factor D. Now, if we do something slightly subtler here, you do 3 EJ, J plus 1, J. Well, then if you just draw the picture, you see this is topologically equal there. And that's what Temperley-Lieb didn't write it in this fashion, but that's their algebra. And why this algebra is so important for people to do statistical mechanics is that this same algebra occurs all over the place. And many of them integrable. I'll say a little bit more about what integrability is later on. Okay. So this algebra occurs in lots of models, not just this geometric model. So before getting to the other kinds of models, though, I want to say something about integrability. So the canonical way to study integrability these days is to show that the Boltzmann weights satisfy the Manning-Baxter equation. So I'm using the same graphical notation I used a few slides ago, where for the example here, we just replaced it with the 2 avoidances. In more complicated models, you do more complicated things. And then you draw this thing there. And again, I introduced this parameter U that parameterizes the weight. So these weights at the different vertices here, the different place where these lines meet, can be different, although not completely different. I have 2 distinct ones, U and U prime, and U plus U prime. And this relation is understood as being in the evaluation, but just for convenience, I'm not going to write it out again. And so anyway, so what it means is what we want to do to show a model is integral to show that the Boltzmann weights satisfy this relation. In other words, fix V and H and D so that this equation is true. And so let me just say for 2 seconds why this is interesting, because you notice in this equation, U and U prime have changed places on the 2 sides. And what this relation is used, the genius of Baxter in figuring this out, this can be used to make commuting transfer matrices, and that's one of the signs that models are integrable. You have these parameters U basically that parameterize a commuting transfer matrix, and that's how you show the model's integrable. I'll say more about that later on. And one thing that as a comment that might be a little bit useful later on too is that if you think of U and U prime as angles, then this picture makes sense in all three. So if you've ever done this, it's especially for one of these height spin models that I'm going to introduce soon. It's just wildly over-constrained. Lots of equations for very few unknowns. We just have V and H, and D isn't D. Well, D isn't even a function, and so we basically have two variables, U and D. And so shockingly, there is a solution of this. There's the equation. So first of all, you see that despite lots of equations, when you use this fact that closed loops give you a factor D, it reduces only to one equation for the ratio of the two H over V. So it's still a functional equation. It's nonlinear. Notice there's 3 W's there, 2 W's there. So still horribly nonlinear. But if I just write D equals minus Q inverse, that's an unusual parameterization, but it's just easier for this. Anyway, so you just parameterize it by D as some number Q minus Q inverse. Well, then if you can just see that you plug in that weight, and that solves that nasty functional equation. So that's a remarkable thing, and people again observed this in the in the 70s, some version of this in the 70s, and I'm not sure. Well, people, I don't know, expect miracles to happen in physics, but I think it's a miracle that something so simple arises from such a complicated equation. All right, so now let's move up to the 80s. Now, I'm going to give a very cynical physicist view of what Jones did. From my, well, not even from a crude physicist perspective, I wouldn't even say, but for purposes of this talk, what Jones did was say, let's take the Temperley-Lieb algebra, and it also gives representations of the braid group. And what that enabled him to do was compute knot-and-link invariants. Now, I believe, since David is the organizer, I think someone told me that David was the one who told Jones about Temperley-Lieb, and so David can deny that if that's not true, but I'll give him credit anyway, was the one who, Jones did this work not knowing about Temperley-Lieb, and David told him about it, that they got at least to some of the story decade before, more than a decade before. Anyway, so let me show a little how that works, although this I'm going to go through really quickly because I'm assuming that pretty much everyone here understands how to do this. So what you do is just like I did with the loop model. I draw this other thing, which is an overcrossing, and then another thing, which is an undercrossing, and I resolve it in the same way, and I fix V and H to be this number Q, or to the square root of Q. And so if you like it algebraically, that's saying what the braid generator is. And again, so you take your knot and link and you resolve it into a sum of closed loops, just like I told you about for the stat-mech model. And to get the Jones polynomial, you just replace each loop with this minus Q inverse, and then that's the Jones, almost the Jones polynomial. Okay, so again, stop me if I'm going too quick, but I think everybody, I hope, well, at least most of the people in the audience have seen this. And so then Jones checks that you have to satisfy the Reidemeister move, so two overcrossings. Sorry, an overcrossing, undercrossing gives you nothing, because you can just drag the one on top over and just plug in the definition I said, and you get these things, and then you evaluate the closed loop, which gives minus Q inverse, so you get that again. So it works beautifully. What's the point, so the third Reidemeister move says you drag the guy in the middle over to the other side. So you see, you drag that one there, and it looks like that. People sometimes call this equation the Yang-Baxter equation. I've heard it. It's not. It's the third Reidemeister move. The Yang-Baxter equation is a more complicated equation. Obviously, they look the same, but Yang-Baxter equation has these parameters that I emphasized a little while ago. So it's a more complicated equation. But what people observed after Jones's original work, that lots of examples you could now find, and by taking limits, and the one for Temperley-Lieb and the parameterization I gave you, you take this parameter U to be I infinity, and you get the braid or braid inverse. So there's one other thing I want to use. It's ironically the simplest of the Reidemeister moves is not quite satisfied. But for my physics that I'm going to get to at the end, this is an interesting thing. You have the overcrossing, the twist, and then you plug that in and it doesn't quite work. You get this factor here, Q. And since Q is often a root of unity in all the examples I'll study, it is. I'll study these later, is this is some phase. And the way people pointed out, or Jones pointed out, you get rid of this is you have to do the writhe. And normally if I give talks to physicists, this is when I stand up and take my belt off and twist it around to wake people up. But I guess I'm not wearing a belt. I'm just wearing sweats, so I can't do it today. All right, so now let me get to the second class of models that I'm studying today. How many? I need to see a clock. Okay, we're good. So now the second class of models are these height models. And since I've taken a lot of time trying to explain this carefully, the setup carefully, I want to go through this quickly, but please stop. So what these types of models are doing is, instead of looking at degrees of freedom, these geometrical degrees of freedom like loops, now we just have discrete degrees of freedom. So like for Ising model, we have something that takes values plus or minus 1, and we put them on the sides of the square lattice. In that picture, why I labeled those points on the dual lattice before, that's where the heights live. And for Ising model, you then get Boltzmann weights over the configuration. So again, for each square on some lattice, and I'll have more pictures in a second, you get a Boltzmann weight that basically weights differently whether the two are the same or two are different. Now for Ising, I did something perverse. I've drawn on a square lattice, but only occupying half the sites. That turns out to be convenient for later reasons. So here's the same picture that I drew a few slides ago. This was the original thing, but now I'm going to put heights living on these faces of the lattice, which the faces of the lattice that the loops live on. And if I make my Boltzmann weights depend on all 4 heights around one of these quadrilaterals here, then that's the Yang-Baxter equation written there. And this is the Yang-Baxter equation for model. So now here everything's local. So these stories mesh, and height models obeying Temperley-Lieb were again observed around the same time as Jones, slightly before, by Baxter, and then a whole series of them by Andrews Baxter Forrester. Lots of beautiful work in the StatMech world in the mid and late 80s. Now, again, this is a category talk, so you may have heard of this under the name shadow world. So what it does is it relates these geometric objects, these geometric models that I talked about before, to these height models. And again, in the algebraic language, this was known in the physics world, and then Turrive and Jones, and then Turrive generalizing, lots of people generalizing, showed how to do it in the shadow world. And I mentioned in the beginning, this was reinvented and renamed 10 years ago. So for the experts here, the models that Andrews Baxter Forrester did satisfy the Temperley-Lieb. It's a category that people I think now call the K+1 category. It's like SU2 level K. It doesn't have a Frugini-Schur indicator, so it's a little easier to deal with, but it's essentially the same. But the key thing is you have heights that take values. We start counting at 0 because that's associated with the identity object, and run them up to K. And so these are discrete variables. The key thing is when you're taking one of these height models, you let them run from 0 to K. Okay, so if I do A3, so it goes 0, 1, 2, but I have a rule that adjacent heights have to differ by 1. So now this is why this one's the Ising model. I wrote Ising in this funny way where it was on different lattices. So notice on one sublattice of the square lattice, it's always this height 1. And so on the other one, you have 0 or 2. That's 2 values, and those are the Ising values. A more fashionable one these days is people sometimes call Fibonacci. And that, or sometimes in the old days, it was called hard square. In the Enneon chain language, people call it the golden chain. There you have 3 possible heights. And again, they always must differ by 1. So you get, there's a configuration like that. And there is what the Temperley-Lieb generator is in terms of the heights. And so let me just, so I'm showing this so you know it's true. So you can show that these things satisfy that. And that's what, essentially what Temperley and Lieb did, and then a slightly different model that Baxter came up with. And then if you wanted to do the same sort of pictures I drew before, you would get something like that. Or I should say the dual pictures, and you can get Hamiltonians out of it too. All right, so finally I can get to now what good this is. So we study a wide class of models where you define them using a fusion category, and I just flashed a few examples there. And the traditional stat-mech languages, like I say, using these algebras. There's a new language for a few people might like. It's what people now call tensor networks. It's really the same thing. Let me skip that. Sorry, since I don't have a ton of time. This, if you can read this quickly, or it'll be on the slides if you look at it later. This is how to relate it to tensor networks if you want to. But the reason why I want to do it is because, as all the category people know, you get this, the tensor category gives a set of rules that allow these graphs that you get, like the loops, to be manipulated without changing the evaluation. So just like replacing over and undercrossing with the sum, there's lots of rules you get. And here's why I like it for the rest of this talk. You can get lattice topological defects out of these things. And that's what's really, well, I think amazing, powerful. So, and so it's absolutely systematic in any model you define using these things. And I forget if I wrote this thing, but basically any rational conformal field theory has some underlying lattice model that can be defined using this some fusion category, usually multiple ones. And for any of those models, you can find exact lattice topological defects. And once people had worked out by brute force some of these things before us, but it's very difficult because the equations are really nasty. And so not only does it give an easy way to find these lattice topological defects, it's almost instant once you do what we did, but you can get topologically invariant junctions of these lines. You can get lots of duality, generalizations of Kramers-Wanier duality. I won't say much about that, but if you may have heard of G factors for conformal boundary conditions, you can derive these exactly. So it's a universal quantity you can derive exactly on the lattice. And you can also get exact dimensions of operators. So now for the rest of the talk, I'll try and illustrate some of these things that we can do and give a little more detail of this slide. All right, so what about 20 minutes? Good. Oh, plenty of time. Okay, so let me explain what's going on. All right, so here, let me sort of review what I said before. So I'm going to mainly talk about, for the rest of the talk, the local models. So these models have degrees of freedom living on the sites of some lattice. They have a Boltzmann weight that depends on the 4 heights. And I'll write out some explicit formulas if that isn't familiar to you. And so then what I want to do, and so I'm going to insert a defect. And so I'll say, I'm going to have some defect. I'm going to take that, make that the path of the defect. And so I'm going to tell you how to define now the partition function in the presence of the defect. And what we do now, okay, so the way you can imagine doing this is, okay, here's my defect's path. I crack open the lattice like this. And then I insert these Boltzmann weights. So now notice what was one, so if I had this vertex here of the lattice, well, that's here. Now, I remember I said heights live on the vertices of the lattice. Well, now what was one vertex of the lattice is now 2 here. Maybe we should go here, 2 here. And so now I've increased the number of degrees of freedom. And then I have Boltzmann weights. So just like I have Boltzmann weights for what configurations of heights are on this lattice, I have, on the bulk here, I have some weight for this defect line here. And so here's the partition function. So if in the absence of the defects, just forget this. So the point is you've got some number associated with depending on which 4 heights live around each face of the lattice. So you take that some number, you take the product over all of it. Now, if we have a defect too, we just then have 4 heights around each defect bit, or each bit of the defect, and then have some number there. So you take the product of all of those numbers, and then you sum, like you summed over all loop configurations in the geometric model, then you sum over all the allowed height configurations in this model. So that's schematically what we do. And what we want to make topological defects. And so what that means is the partition function that I just defined is invariant under deforming the path of the defect. And in the picture I had here, what that would correspond to, say, moving that up to there. And so that's what that looks like, so as we can do that. And so what they do, or this one is moving it, if it runs along a face like that, you make it go around like that. And so since in the partition function we're summing over every allowed height configuration, what we really need to get this quality, we don't need these two things to be exactly equal. What we need is when you sum over the internal one, that they're exactly equal. So this is the defect commutation relations. They're similar in some ways to Yang-Baxter, but they're not the same. If you want something that looks like Yang-Baxter, that's what it is, and that's what tensor network people would draw. So anyway, so the great part is I can now, with the setup of the fusion categories to define these lattice models, I can write down the answer. Literally no more work other than the proof of this formula. So I know exact lattice topological defects. So for any object in the category used to define the lattice model, that's what this phi is here, I have an answer, and the F's are the F symbols of the category. So it's a known thing, the category hands you that, and there's the answer. So in any of these models, and these are exact thing. If the category has braiding, the answer is easier, but if not, you talk about the Drinfeld center. For people who know about the icing category, there's, well, a couple defects I'll talk about in a second. All right, so the proof of this thing is stunningly simple in this setup. So I just drew the diagrams there. So the point is you define all the Boltzmann weights in terms of categorical objects, these pictures, and you just define the defect weights and turn them, and then you manipulate these pictures using the rules of the category, and then you get to move it through. So this one, notice you see it says here, notice you have this one, and you do a bunch of manipulations. So this one looks like that, but notice we've moved the defect line over the other side. I can obviously start with there and go to the other, and that's the defect line commuting through. So this is schematic, but I hope at least gets the point is, once you define these lattice models using the categorical data like Temperley-Lieb, then this stuff is all automatic. And one thing I emphasize why is you don't need to impose integrability, because this, for example, works for any choice of coefficients of the projectors when you write out the Boltzmann weights. And integrability requires special assumptions about that. Typically, in these models, there's a special case that's integrable, and they almost always turn out to be critical as well, but that's not a requirement to get what we're doing to work. So let me flash what's going on in icing. That's just the Boltzmann weights I wrote. Again, remember there's this funny thing where with icing, I chose this convention where the heights lived on only every other side of the square lattice. And if you remember, that was so I could turn it into this A3 category where it was 0, 1, 2, and the A's and the B's are 0 or 2, and then this was 1, and in usual conventions for icing, you would, instead of 0 and 2 would be plus or minus 1, but same idea. So here's what the spin flip defect, which is associated with the psi field, if you know something about the category. It just says this Boltzmann weight. I drew it red to distinguish it from the other defect I'm going to get to in a second. Just says, well, when you cross the defect, you just flip the spin. So that's what 1 minus delta AB. You get 0 if they're the same, 1 if they're different. So that's what a spin flip defect is. And that's pretty obviously topological defect. People, again, knew that by brute force for ages. Not as obvious, but known in the icing world, is what happens when you have a duality defect. And here's where the setup, where I ignored these other sites, is good. Because notice here, this preserves the same lattice. Remember, these 2 points came from the same original point on the lattice. I split it into 2, and this is just saying, well, when you cross the defect, flip this one on this side to, say, plus on this side to minus on that side. But a duality fix switches sublattices. So when you have a duality defect, and look at which sites are the plus and minus, or the 0 and 2 in the other picture, it switches on the sides of the defect. And also it switches the value to the dual coupling, which is not obvious, but you can work out. All right, so that's an example for icing, because maybe that's familiar to some of you. But if you're not, well, all I can say is then you don't really need to know that. If you know something about categories, then any lattice model I define for categories, which is a high percentage of the lattice models studied in the integrability community, as a high percentage of the critical integrable models studied in the community, and then many generalizations thereof, are with these. And so now we can do these defects, but these defects not only are topological, they have all sorts of marvelous properties. It turns these defects, if you wish, into microscopic rules, these fusion category rules in there. And so remember our microscopic rules when we had a closed loop, well, it turned in to this number, this D. So now we have something else. We have this label phi in a defect. And again, category people, this is just called the quantum dimension of the object phi in the category. And when I make a defect, it's easy to check using the defect commutation relations and the explicit expression that this thing, if I have a closed defect of weight there, well, I can just get rid of it. And all it does is multiply the partition function. So what I do is I have some partition function for this. So this is my schematic notation for a partition function with a defect. And whatever thing is, but I can use the defect commutation relations to shrink it down to just one. The shortest possible, so just surrounding one face, and then I get rid of it using this and there. And so this is an equality between partition functions. Really powerful. It doesn't matter how big the defect is. Can't wrap around a cycle, that's another story, but it does that. And so this is duality. So this is a way of seeing, driving all sorts of dualities. The icing one was known, but not in so general a form. You can fuse defects together. They follow the same rules as they do in the category. So if I have two duality defects, I get one plus the spin flip defect. Again, if you know the icing category, that's the basic relation of it. If you don't, just trust me, that's what the category tells you. And but what it's telling us in our defect models is that the partition function with two duality defect lines surrounding each other is equivalent. Well, it's the sum of partition functions of having no defects plus just the spin flip defect. This is this more complicated hard square Fibonacci category one there. And so it gives what looks similar, but isn't the same. This one is these two of them, and it just gives the same one back again. Fibonacci. And one thing that's one of my major pet peeves when people talk about Kramers-Zwanny duality in physics is people often call duality a symmetry, but it's really not. And this setup makes it clear why it's not unitary. For one, symmetries in physics we usually want to be implemented by unitary operators. And in fact, in icing, it's not even invertible. So there's just no sense in which it's a symmetry. If you remember the physics of the icing model, this is why the low temperature phase has two ground states and the high temperature phase has only one. The mapping isn't invertible. So let me just flash this in case you can compute these G factors on the lattice. So a few of you who know conformal field theory may know something about this. So basically the point is you can say lots about boundary conditions. You can change boundary conditions in a nice way by gluing the defect to the boundary. And it fits in beautifully with Carty's boundary state formalism, and it gives you a formula for relating the partition functions with different boundary conditions. And again, this is all instant. I mean, once you know what the category is, this basically all follows, well, from the proofs Dave and Roger and I made, and by then just knowing the stuff about the category. It's really that simple. And so this is the G factor for a few of you who may know what this is. So pass over that. And so the defects, like I mentioned, they satisfy this rule, this microscopic rule of the evaluating a loop and getting a weight D. Well, the defect lines themselves also satisfy branching and fusing rules. And so again, there's something like the defect commutation relation. So now, like we split open the lattice before, well, now I have a junction of defect lines. And the way I split open the lattice there is to have a triangle defect on my lattice. And then I need a triangle weight. So there's some weight there. And then it has to satisfy this thing here where you commute it through. And then you see, once you do that, you can move this triangle defect around, and you mess around a little more, you can then see that the defects themselves obey the F move. So if I have some defect configuration like this, it's the same as the partition function there, where the F moves coming from the category tell you exactly how it does. So I find it just, when I was stupid, Dave and Roger told me this, and I didn't believe them to begin with, but it's just remarkable. Let me flash another quick one before I get to the one bit I wanted to linger on for a little bit. Again, you can talk about this on the torus, you can do duality on the torus, and in fact, we have a general formula to a conjecture, I should say. So this we haven't proved. What we conjecture is that if you take a partition function of a conformal field theory, which is written in this form, these are characters of or some extended algebra, and M is some matrix with integer coefficients, symmetric matrix typically, of integer coefficients, to give you the partition function of this conformal field theory on a torus. Well, by matching what's going on in the lattice and these boundary conditions and these defects that we can understand on the lattice, you can come up with for an exact formula for this M in terms of various objects on the lattice. Now, it doesn't give everything, but basically this the ZABC. Sorry, I didn't put that there. This is the partition function of the lattice model with a particular defect configuration. And then this relates the corresponding continuum thing. So sorry, that's quick, but I just wanted to advertise that. So, okay, for the last 10 minutes, I wanted to not go so quick and say a little bit more about something that won't appear in the paper in a few weeks, but hopefully not too long. And this goes way back. And remember, I made a point when I was showing the third Reidemeister move to say that, well, the Yang-Baxter equation and the third Reidemeister move are not the same thing. The Yang-Baxter equation has this parameter, but obviously there's a connection. So Vaughan asked this question a long time ago in the 80s again. Well, can we go the other way? So people worked out lots of examples where you took known solutions of Yang-Baxter and then saw you could construct some kind of knot and link invariant from them. But Vaughan asked, well, can we go the other way if we know some kind of a fusion category and pick some kind of object? Can we find a solution of the Yang-Baxter equation that maybe we didn't know about before? And as far as basically all attempts to do this until what I'm about to tell you were just brute force. And people found some, but not that many. And it's really an interesting problem because you can't pick an arbitrary object to draw these lines to get things. Most of the time, there won't be a solution to the Yang-Baxter equation. Physicists, by brute force and luck, found, I think, most of the easy ones. There's probably a few out there that are tricky, but there's a big question, even why are these solutions? So Vaughan asked this question, and people always say, did brute force? But I think what I'm talking about in one additional ingredient gives a way forward on this. So let me explain that. So there's something that came up 10 or so years ago, again, in both the math and the stat mech literature which was named somewhat incorrectly discrete holomorphicity. And this was initiated by Stas Smirnov in his beautiful proof that the Ising lattice model becomes the Ising conformal field theory in the limit. Basically, he found certain operators in the model, for those, the Ising models, the lattice fermion operator, but he proved that it was holomorphic in the continuum limit and used that to show that it gave the right conformal field theory. And so what he showed is there's some operator you define in the lattice, and you take the expectation value of this operator around some closed path, and you get the answer 0. So that's like a Cauchy-Riemann equation, saying this operator only depends on Z and not Z bar. And let's say the fermion operator, the Ising model, there's other known ones. So so Smirnov thought this was great. He did this rising and then instantly came up with other models that satisfied this relation. And then Cardy and collaborators came up with lots of nice ways to find other. But the key thing is it's only half the lattice-Cauchy-Riemann equations that this satisfies. So let me try and, I didn't have a slide with the square lattice. Sorry. So the reason why this is only half the lattice-Cauchy-Riemann equations, because if you think about there on a lattice, so this is surrounding each. So the way we define these operators live on the edges of, say, the square lattice, but this relation applies only to each face of the square lattice. Well, there's twice as many edges as faces. So you can show that it satisfies this, and that's great and nice, but it's only half the Cauchy-Riemann equation because there's twice as many degrees of freedom from the lattice. So that's why it's only half. For Ising, there's another one. So there are the same number of constraints as there are degrees of freedom. So that's why you can prove what he proved. But all these other examples, they only found one. So that's why I said discrete holomorphicity is not a good name. You know, like being half pregnant, you can't be half holomorphic. You either are or you're not. And so this isn't enough. But then so then the question is, well, what good is what they did? And there was something good, and I'll explain about it. But so the Cardy collaborators kind of did this by brute force. But my point is that once you do categories, there's an easy way to find such, or at least candidate operators for these things, and show that they have nice properties. And that's why I singled out this writhe that comes up in the first Reidemeister move, this extra factor here. So this is exactly what you want to get some operator to have the right properties out of these things. So if you want these operators to be discrete holomorphic, so now I'm just writing down the same equation I put on the first slide, what Smirnov did there. So basically what you want is to have these operators. So we take now a topological defect, we terminate it on an edge of the lattice, and the category gives you a nice way to define such a thing. And then we want it to satisfy this thing. So what this equation is here, what they called the discrete holomorphic equation, was to sum over the 4 different configurations like this, and where the dz's are just the distances there. I drew it in the square lattice, but you can generalize it to others. And so this is in hopefully category type pictures, what they call the discrete holomorphic equation. And that's what it is. And you can do it for the height models that I spent a lot of time talking about too. So Cardy now, in looking at, so they found all these solutions. What didn't work for the Ising. It didn't work to prove what Smirnov proved. It did work for Ising. And so, but what he wanted to show now, well, what good is it for? So he said, okay, well, I've got this nice relation. Now let's think about this. First, let's define these operators the way I would do in the category theory. And then I have this Boltzmann weight here, but instead of picking my lattice model and thus determine the Boltzmann weights, I'm going to leave that undetermined. Okay. And then he says, now I'm going to find Boltzmann weights that satisfy this equation. And then what he found was that these Boltzmann weights that satisfied this linear equation, because there's a linear equation for the Boltzmann weights, that there's only one of them there. And I find a solution to this equation, and then I just check, and this solution satisfies Yang-Baxter. And in more complicated models, it's not, I drew the simplest example of this loop model, but much more complicated models there. And anyway, so in a way, it's the opposite of what Smirnov said, I'm going to take some model, and then I'm going to show it satisfies this. Cardy said, let's leave this undetermined. I'll basically use the category data. He didn't say it that way, but that's the way I think it really is. I mean, that's what he's doing. And then we get this thing. And so it's now a way forward on Vaughn's Baxterization problem, which is that this is a linear relation. operation. And, but then if they satisfy this, they satisfy that. Now, that may seem a bit crazy, but you have to remember, I mean, the category is highly constraining what's going on. So let me just write out what's going on here in this one example. So I define these operators in Temperley-Lieb in a really simple fashion. So if I want to stick in a 2-point function, what I do is I use the braiding. So let me draw without the braiding. I stick in my topological defect, stretching from here, but then I terminate it there. And then the way you compute this is, well, now I just have a 3D graph I evaluated in the category with it there, and then otherwise everything is exactly the same. So that's how I define that object. And it's even simpler when you write these things out in terms of loops. The point is you can't have tadpoles. So the two ends have to lie in the same loop. That's the rule. And the twist factor that I mentioned all works out if you define it within the category. So what it does is give you, if you can solve this equation in the category, and everything here is defined certainly in a braided category, and I think you can do it using the Drinfeld center, even a more general category. If I can find a solution to this equation, then in all the examples I've worked out, it also satisfies Yang-Baxter. Now, since I ran out of time, I omitted the slides. What you can see is what this does by you is it's a conserved, it's related, you can define a conserved current if it satisfied this is. So this is why it's maybe not shocking that if you satisfy this linear thing, you get this special thing. It's showing there's an extra funny, unusual conserved current in these lattice models. And thus, the fact there's more symmetry and maybe the fact that the model is integrable is that the Boltzmann might satisfy this Yang-Baxter equation isn't so surprising. So that's the motivation. All right, so sorry that was a little rushed, but I hope at least I got the point across. Let me say some other things. I think I said in the abstract I was going to get to this and only preparing to talk really there's no hope, but you can say interesting things about combinatorial problems. It's Slavin Krustal and I wrote some papers a while ago now, and a new paper about a year ago with some others in the works, to use this sort of category to generalize this Potts model stuff further, to go back to the Tutte polynomial instead of the Potts model and say interesting things about that. There's lots of interesting questions about conformal field theory. One thing I have to put in an ad for poor Vincent Pasquet. Vincent Pasquet did all this amazing work in the 80s, prefiguring this before the category language developed. And among other things, he found an explicit example of the Verlinde formula before Verlinde did. In fact, if you look at his paper, I mean, it's written with N's and S's, just like Verlinde. He didn't understand it as generally. He obviously didn't understand how deep it was, but he really, it's there. So, Pasquet thought a lot about conformal field theory in the lattice, and now we have some tools to go further than he did. I think just taming the zoo of integrable models would be a good one. So this question I mentioned a few seconds ago, I'm not sure for what I showed you at the end. For the topological defect stuff, we have a better control of what category data we need. So I think we're not quite sure of what the minimal amount of data we need is. I phrased it using braiding, but I suspect we might be able to do better. And then, however, I guess Tobias Osborne is going to give a talk in this seminar series in a month on that. Maybe our paper will be done by then and he can comment on something useful. I'll just trying to think, this is the crazier stuff at the end. Yeah, let me just go to the last one. Yeah, so I mean, I think this is real progress in I think just thinking about categories is a useful input. Like I started out saying, the people in the stat mech world, I think mostly neglected the whole category story since at some point in the mid-90s, moved on to other things. And I hope this talk and the papers that we will finish soon will be a motivation.